Structural Analysis 2, Chapter 8, Deflections using Energy Methods. Let's solve an example in trusses. So in this example, we want to determine the vertical displacement of joint C. So this is joint C, and we want to calculate the vertical downward displacement of this joint. If the steel trusses presented below, every member has an area of 5 inches squared, and modulus of elasticity provided for steel to be 29 times 10 cubed KSI, kilopound per square inches. So before solving the problem, let's see if we can solve this problem with the work of with the work and energy method. So that's a real work method, because the effect of force is at the joint. So there is a 4K applied directly at joint C, and we want to calculate the downward displacement, and we have a force applied there. So at the very first glance, it seems that we can solve this problem with the with the help of work and energy method. But the point is, because if this 4K was the only force applied to the structure, that was fine to solve the problem with work and energy method. But because the other force also has an effect on the vertical deflection of joint C, so there is a limitation of work and energy method. If you have a force applied at the same joint and you want to observe the same direction of your force, and that's the only force on your structure, you're more than fine to use the work and energy. But if there are some other external forces applied on any other location, they also have their own effect on deflection of that joint. Maybe that effect is even small, but yet there is an effect on there. So you're not allowed to use work and energy method. So you need to virtual work. So work and energy method has a lot of limitations, that you should have a real force at the joint you want to observe, and at the same time there should be no other forces on the structure. So there is no way but to solve it with the help of virtual work method. So if we want to solve this problem with the help of virtual work method, first of all, let's develop a moment about point A to calculate AY and DY. So if you do so, it just gives you a DY equal to 4K. And due to the symmetry of a structure, AY should also go by 4K. If you don't agree, you can solve it with the summation of forces in y direction. These two supports should cancel out. These two, a combination of 2 4 kilopounds or kilonewton forces. So if you have dy, then if you just look at the nature of the joint A, for example, let's make it a bit clean here. For example, if your next note is when you're observing, for example, joint A, for example, here, if we do have a AY of 4K applied here, definitely this force should be cancelled out by effect of a downward push, should cancel out this upward push of AY. And whenever you're looking to a joint, the same force applied the joint, it should be applied to the member as well in the other direction. So if this force is a compressive force applied to the joint, the same compressive force. So if there is a compressive force to cancel out AY here, there is also a compression field in the member. So the same. So this is a compressive member. So with this in mind, let's go to the structure. So at joint A, we do have this is joint A, we do have 4K upward force. It should be cancelled out by a downward push. So it's pushing up the joint A upward. So the other force should downward, should be a push to the joint A and also downward. If you project it to its component, so you can easily see these two components as well. If this is for a, then if you want to know what is the amount of this force, so if this is a for a, this is 10 feet, this is 10 feet. So for the length of 10 feet, we do have 4K. So if the vertical component is equal to 4, let's see, this is 10, this is 10, so the hypotenuse would be 10 square 2. So that's a 10 square 2 should be, the force would be 4 times square 2, which is a 5.66. So this is a negative compression 5.66. If this is a push to the joint, is a push to the member, so that's a compression force in this member. And if you make a closer look joint, you can easily see also this component should be cancelled out by a just pushing it. There should be a outward to cancel this vertical component over here. So if that's the case, and that's also equal to 4K. And if this force is pulling the joint, if this force is pulling the joint, it should also pull the member as well. So this is a tensile member and the numeric value is positive 4. And now if you look at if this is a negative 5.66 due to symmetry, this is also negative 5 because dy is also 4. If this is 4, this is 4 as well. And just look at the joint B. If there is a 4K applied at the joint B, there should be a upward for joint B, which is also pulling downward the member. So the member is tensile member, and that's a 4K force inside. Definitely, you can easily see this force is cancelling out with this force is cancelling, and this is a 0 member. So the same story happened on the other force. So these are the effect of real forces. So so far we calculate capital N in virtual work method, which the formula for that is 1 virtual force times delta C at V, delta C vertical is equal to summation of N times N virtual times real force times the length of the member over EA. So we want to calculate this formula, and right now we are in this part of the problem. We are calculating structure due to effect of real forces. So if you do so, you can have all the forces like how it applies to the members. Now, in the second step, we just move on and apply a 1K kilopound force in a joint C, like a downward 1K force, virtual force, and then again see the internal forces applied to the structure. So again, summation of moment about A goes 0. Definitely if 1K, just assume this is a beam, if 1K is applied to a AD beam, definitely the bigger chunk of energy of force goes by dy, so that's the 2/3 of force, and ay is 1/3 of 1K. So you can also get it from summation of moment about A goes 0, and it just gives you dy equal to 1/3 of 1. Then as soon as you do the math, it just gives you ay is equal to 0.100. dy is equal to almost 67K. Then go with the same approach for joint A. If AY is an upward, so it should be cancelled out by a downward push, and that push, it just create a push in the member, so definitely it's a compression member. So again, if by the length of 10 feet, or this is also 10 feet, this is also 10 feet, so if by the help of 10 feet we just go for a 0.3 for 10 square to x is equal to this number, which we have it over here. Also, as soon as we have this one, we can easily calculate other forces. So if this is a tensile force by the, if this is 10, this is 10, this is 45. By 45, it means if this angle is 45 here, it means these two are the same. If this is a push to the point joint, then there should be a force cancelling out that force by which pulls the joint. So if it pulls the joint here, it should pull the member as well. So the member AB is a tensile member, as you can easily observe from observing joint A. It can easily gives you a tensile force in member AB. As soon as you have that one, you can easily jump to joint F, for example. If it just point F, if there is a push to joint F from AF, it should be cancelled out by a push to F from the member, so that member is a compression member. And also, if this is upward, it should be downward. So again, if it pulls the joint F, the force in member FB is again a tensile force by the same amount of AY, because the vertical and horizontal complement each other makes a 45 degree angle. And again, can joint B, if this is a upward, it should be a push, and these two angles remain the same. So if this is a negative 0.471, it's also a tensile, a compression force by the amount of exactly amount of 471. And if that's the case, you can simply jump to the point C. At point C, there is a 1K downward, so that should be cancelled out by a upward, a pull the joint. If it's pulling the joint, it should pull the structure, so that's a positive 1K. For the other part, it just, this is 2/3 of 1, that's 0.66 almost. So if for 10 goes by 0.66, 10 square to, which is the length of this member, it just goes by x is equal to a compression force equal to 0.9. This is also equal to 0.66, and that's because this is again 45 angles. As you do so, it just says you have all the forces, and these are the effect of virtual work. We already calculated capital N and now lowercase n. If you just multiply them by each other and multiply by the length of each member, you can easily calculate the vertical displace of delta CV. Let's see how we can do that. As soon as we have all the members, we can create a table like what you can see here: effect of virtual, effect of real work, length of each member, and then the multiplication of the last three columns. So this is the real force effect which we calculate at the early of the problem. This is the effect of virtual work which you applied a 1K at joint C, calculate the internal forces inside the structure. And just for example, if you want to observe or double check the problem. Let's just go for AB. Effect of internal forces for virtual board is gives you point almost 33. So let's jump to virtual force for AB. This is AB, and you can easily see it's a tension and a positive 30, almost 33. If the same member for a real forces, it just gives you a positive force. So we have positive force. Let's double check FE, for example. FE is here. For virtual work, we just have point negative 33, and for a real force, we have negative 4. Let's observe CE, for example. Let's see where CE is. So this is our CE. The effect of CE for the virtual one is small lowercase n is a positive one, so we have positive one here. For the same member in of real forces, we have positive 4, and you have it here. Length of a FE, which is again 10 feet, and if you do lowercase n capital N times the length of the member and you add all of them up together, so it just gives a summation of total of 246.47. And if you jot down the equation, it just gives you one virtual work times the downward delta C vertically summation of n times n lowercase n capital N length of member. Okay, so we have numerator from here, and if we just replace EA from the problem statement, like what we have, all the member areas are 0.5 inches squared, and E for steel is 29 times 10 cubed KSI per inches squared, and if you do the mass, it just gives you a downward delta C almost equal to 0.2 inches. Thank you. Solve more problems. Virtual work energy method. Thank you.